Okay. Welcome everyone to our talk. We will essentially do a continuation of the talk that we did last year at KVM Forum, talking about SVSM and from where we left to essentially to support persistent state to discuss about potential new services. Before going into the detail, just to recap why we need SVSM. I will go pretty quickly since the talk before us already covered parts of it. So essentially, in a confidential virtualization environment, we need kind of execution environment that should be trusted to provide secure services to the confidential VM. So we are certain kind of services and devices that cannot be, that usually are emulated by the host, but since we don't trust the host at all, must be in some way run inside the trust compute base of the confidential VM. And one example is the one that AMD defined in the SVSMP specification, which is called Secure VM Service Module, SVSM. And the services, the potential services that we want to run are, of course, emulating the vTPM, but also provide the storage services, the UEFI variable storage, and also an helper to support live migration. And what we are working on is COCONUT SVSM, which is written in Rust. Was started in 2022. We are now part of the confidential computing consortium, and of course, from the name, we started supporting AMD SVSMP, but we are also now working on supporting TDX. And the VMMs and hypervisors that we support are QEMU KVM, Microsoft Hyper-V, and also Google Vanadium. And currently, the current implementation provides an attestation service, an APIC emulation, a virtual TPM, and also we are working on UEFI variable storage. Gerd talked about it yesterday. Currently, to work with SVSM, we require an enlightened guest, so you need specific driver to talk with SVSM, but a paravisor mode is in our plan. Long plan. Let's do a quick update on the last year development in COCONUT SVSM in the community. So the first things I would like to mention is, let's speak here, is the essentially till some months ago, we had only one maintainer, which was Jörg Rodel, and he decided to extend the maintainer base of the COCONUT SVSM project, essentially mainly to share the project responsibilities, to improve the project progress, the speed how we do review and discuss the things. And then we are in 4 currently, so there is Jörg Rodel, which is the chair, Jon Lange, Peter Feng, and myself. We do weekly meetings to discuss all the things, PRs, issue, and questions. All of us has write access to the repository, and essentially we have a voting system to when we have some kind of discussion that where we don't agree, essentially. But the chair has the right to override that. We are thinking on, if the project will grow, we are thinking on adopting some kind of sub-maintainer for several spaces. About a feature that we developed. So we mainly focus on improve our security and code safety. So we finally documented all of unsafe blocks we have in SVSM, and we reviewed them. And we also enable, by default, a couple of CPU security features. We started to do a better abstraction of the platform, of the architecture. As I mentioned, initially it was based only on AMD SVSMP, but now we are really working to support also TDX. And also we improved a bit our multi-core support. And also, as the previous talk talked about, we are working on supporting a user space in SVSM, because currently all the services run in kernel mode, but this has a lot of limitation, especially on Rust, because we must use no STD everywhere, which is kind of limitation. And so we are defining a system call interface to support user spaces. So the idea is to move all the services and device emulation to the user space. We also started to support vert.io, mainly thanks to Oliver. The first driver that we have is a vert.io block, and Oliver will talk a bit more about it. And we are also working, Luigi is working also on supporting the driver for vert.io VSOC. And other things we did, we essentially changed a bit our build system. So now we have a tool that accepts a JSON receipt about what you want to build, about how to configure SVSM, the feature that you want to enable, the architecture that you want to support, and that kind of things. We improved our CI, and also Microsoft is spending a bit of time on introducing formal verification in critical path, like for now they are focused on the memory allocator. If you're interested on that, they are really asking help on doing this work. And about the ecosystem, so we started to merge support for SVSM in related projects like QEMU, the latest version, bring the support to IGVM, which is for now the only way how we ship SVSM. IGVM essentially is a file format that contains binaries, and in our case is SVSM and OVMF, and also some metadata, especially that represent the initial state of the vCPU. This is really important to simplify the launch measurement precalculation, because it really depends also on the initial vCPU states. So now the upstream QEMU can boot IGVM. Can boot SVSM. Also, we are also working on supporting vert.io and MMIO devices for SVSM. So essentially, we need a couple of devices assigned only to SVSM. So Oliver sent a series we are discussing upstream to do that. And about ADK2, the version from May support the TPM driver. So we can say that ADK2 is basically SVSM ready. Something similar also for Linux. The latest release, 6.16, contains the TPM driver for SVSM. And so also Linux can now, this is on the guest side. The guest side is pretty much ready to work with SVSM. And for the host, as also Vashil mentioned, we still need the KVM planes that is under heavy development. And to Oliver.
Yeah, so a big topic that we've been working on for the last year is adding persistent state to SVSM. Some secure way to persist some state is important for the virtual TPM and for other services like UEFI variable store support. Important building block for this is a storage driver, and there we have the vert.io block driver merged. A second part that we need is the attestation driver, let's say, that carries out the remote attestation, because this is the way how we get the encryption key for the encrypted state. And then what's still missing right now is a proper encryption layer and some kind of file system or partitioning of the storage. This is what we need to do next. We need, of course, a good encryption, because the whole disk image, or like the state image, is sitting at the untrusted hypervisor. We need some kind of integrity protection of that state, so that it can't be modified or we detect modifications on it. Ideally, we would also have some kind of rollback protection so that we can't, the hypervisor can't just like feedback some old state on the next boot in this way. Yeah, make a mess. Yeah, we need some kind of disruption tolerance, or like some kind of journaling or something like this. What you need to keep in mind with all of this is a little bit more complicated than just normal FDE that we see, because the hypervisor can monitor all accesses that we do. So it can see where we write and where we read. And this is not always thought about in regular FDE encryptions systems enough. Yeah. So the vTIO driver, yeah, as I said, like this is merged in SVSM. So we're using the vTIO MMIO transport. Yeah, we're using vTIO because it's an existing standard and it's reasonably easy to implement, and it's yeah, well proven. We use MMIO transport, yeah, for simplicity, where it's easier than implementing PCI or these kind of things, and it's also easier to hide from the guest operating system, yeah, because it should also not be able to access the storage. Yeah, for this we need some patches in QEMU because the normal Q35 machine model doesn't foresee vTIO MMIO slots, so we have a patch out for that, where you can enable some MMIO slots with some command line switch. Yeah, currently this works without interrupts, so SSM is polling on this because we are not far enough with interrupt support yet, but we just can change later. Yeah, the drivers, we reuse an existing crate, a Rust crate for vTIO drivers. This is actually pretty convenient. Yeah, we also have already identified some things that we can contribute back to that, some fixes that we're not trying to do around like some endianness corrections that we're thinking about. And yeah, for right now, as I said, we use the vTIO block for storage, and we also have a pull request that wants to make use of the vTIO VSOC parts and use this instead of serial ports. Right now we use kind of a bunch of serial ports for different purposes, for console logging and debugger attaching, and the attestation also makes use of a separate serial port. So we want to replace this maybe step by step by some VSOC connections. Yeah, remote attestation is also implemented. I mean, I guess you all know, like remote attestation, what happens is the SVSM gets some hardware-generated attestation report and sends this off to a remote attestation server. It gets checked, and then if it checks out, then it responds with the encryption key for the persistent storage. Since we don't want to implement a network stack in SVSM, we have two approaches to work around that. And one is running a little proxy application on the host. This is what's currently merged. And then this proxy application does the HTTP connection and talks to SVSM via serial port. A different idea would be to run a small bridge application somewhere inside the guest, for example, as an UEFI application, or from some booted Linux that then exists temporarily to carry out the attestation. Yeah, but these are just plans right now. The current implementation, yeah, supports the trustee key broker service, yeah, which is compatible with the trustee attestation backend for boot attestation, or with keylime verifier backend. So, yeah, with this you have done ways to do the initial boot attestation. Yeah, for the encryption and file system, we have some interesting developments going on right now. So Nikolai Stange is working on some specially created file system for the SVSM use case, which in my opinion already sounds quite interesting. So an important feature is that it supports some kind of encryption algorithm agility, so it supports in principle all the algorithms from the TCG registry, so you can pick from them. Yeah, to be flexible. It uses a Merkle tree for everything that it stores to achieve integrity protection and authenticated encryption. So we can be sure that, like, if we can decrypt the state file, that this state was indeed written before by that SVSM and was not modified. With some future work, we could achieve rollback protection with that, but this would mean that we have to somehow persist the root hash of that Merkle tree somewhere. It could be sent back to the attestation server, or this is always the problem. Where can we put this this hash to store it between reboots? This is still an open thing, but we could, if you have an idea, we could achieve the rollback protection with that. It has a journal to recover from disruptions, and also a nice feature is that has a fully randomized encryption IVs for each file and each write. So files are usually written and read again as a whole, and each time you write a file, you get a fresh IV for the whole file. So this increases the protection a lot, because you can't correlate old and new content of a file. It also supports cryptographic subkeys for different files and different purposes to limit the key wear out. It uses a rather simple file naming scheme. It's just 32-bit integers. And files have a fixed size once they're written, so they can't be like appended or something like this. You always have to read and write a whole file. But I guess for our use case, that's actually fine. And it just makes the whole implementation simpler if you write only whole files. So I think this looks quite interesting, and he's working on a PR right now, as far as I hear. So I'm very interested to see something coming from this. Secure services. So what do we have? So currently we have a TPM, a virtual TPM. This is currently stateless. So every time we rebooted, it lost everything it knew. So it lost its identity. Comes up with new primary keys. So our goal is like to persist that the TPM state, so that it behaves like a real hardware TPM kind of, so that we can support existing TPM use cases like automatic disk unlocking and also runtime monitoring with keylime and all these things that they just work seamlessly. Another application is in the UEFI variable store. I mean, Garzarella had a talk yesterday on that. The idea is that the SVSM provides the secure storage for the EDK2 variable store, because OVMF can't enforce the variable security because we don't have the secure management mode. And then SVSM offers a storage service for EDK2. So here's something that you can look at and see it all works. So we prepared a little demo that you can check out if you have an S&P machine. There's a GitHub repository that has build scripts and a nice README that shows you all the things. And in this demo, we use an encrypted state already. Currently, it uses a simple AES encryption, so not the COCONUT as yet, but hopefully soon. And if you set this all up, you get an automatic disk unlocking with the TPM using the KBS attestation service. You get a stateful TPM, automatic disk unlocking, and the UEFI variable store. But this is still volatile because we haven't wired up the storage yet. But its secure boot is already enabled in it. So it's like a nice way to try out how it could all feel once it's all working. So what can we do in the future? This is kind of a brainstorming and idea collection session now at the end. So what can we do next? And some ideas, if you already have a vSoc connection, do we maybe want to have a secure shell where we can log into SVSM for debugging and diagnostic certain purposes? Of course, we could also use this over a serial port or over some other connection, but I think it could be fun or useful, but I don't know if we need it. This is an idea. We could improve the logging. Maybe we have some built-in log buffer that we can read after from the guest OS, or to yeah, we can encrypt our loggings because we don't trust the hypervisor to see all the log messages. But this would then be decryptable after the attestation process. The question is, do we need it? Yeah, some ideas. And of course, a big topic that's coming up is live migration.
About live migration, essentially, the issue we have is the guest private memory can only be accessed into the guest context. So we are working on it, and especially we have two proposals. The first one that Tom and Pankaj from MD showed last year is about adding an additional vCPU that will run essentially only SVSM to do the memory packaging. They show two different approaches, like the mirror VM on the shadow vCPU. I left the link to the slides for more details. And currently, Pankaj is working on the shadow vCPU idea, and they will show a proof of concept soon. We also have another PR, open upstream from Jakub, which, if I understood correctly, is doing a master thesis on this topic. And so he did, it's kind of an experiment and to show how live migration can work. But I think the direction we will take is something like the shadow vCPU that Pankaj is looking at. And another things we want to work on is SVSM bus in Linux. So essentially, currently we only have one device driver, which is the TPM driver. So yeah, it's fine. But the idea is to support multiple other devices and other services. So essentially, we want, this was an idea started by James Bottling that started a thread upstream that I linked. Essentially, we want to have a way to automatically discover the device, SVSM devices, discover and find the right modules that provide the driver to talk with the device. We want to be, we don't want to be architecture specific, so we want to define an API to talk with SVSM depending on the architecture. Then we need to define a way to identify the devices, like a string or UTF-2. I forgot to mention that this, the idea is inspired to the vert.io bus. So we want to do something very, very similar. And then we need to define how to work with interrupts. So it's not really urgent because the TPM driver is not using interrupts at all. It's a synchronous driver and device. But yeah, we need, of course, to support also that. And yeah, I mean, this last session is more about, also start a discussion. So if you have any idea, any suggestion, or any question, it's your turn.
Thanks. So I have a question about the last slide. So what about just using vert.io as is? Are the requirements different somehow? Why not just use vert.io devices and the vert.io drivers that are already in the kernel?
Yeah, it could be any idea. But essentially our device, I hope, will be less, much more simpler than that. But maybe we can reuse just that part. We need to understand better how to also interact with, for example, the device that vert.io already defines the ID, or maybe just use the architecture but use completely different device. I don't know, to not collide with the specification. But yeah, maybe it could be possible. We didn't think about that, but we can try. Yep.
Yeah, just one more comment, because I think earlier on you said that SVSM now implements vert.io block. So the complexity of vert.io, the driver, but the complexity is already there. You already have the ring buffers and those concepts. So is there really going to be a lot of reduction in complexity if you now invent some new thing?
Yeah, I think the main thing here will be the device detection, right? So maybe using just device tree, if you have MMIO, VirtIO, the device tree seems to be the natural idea to configure the devices.
Yeah, I mean, the VirtIO MMIO is mainly for devices exposed to SVSM, and we want to use device tree to discover that. This is what we want to do. But for the devices exposed to Linux, what we want, essentially we are, for AMD, we need to use the SVSM protocol defined by AMD. For Intel, honestly, I don't know, but there will be another mechanism. So in that case, we need to, for example, for VirtIO, we need to provide a transport, a new transport, which is not MMIO, is not PCI, but could be maybe SVSM.
I think apart from the interrupts, the transport could be basically VirtIO MMIO. Like, okay, not entirely, because one issue is like writing a register automatically jumps to QEMU in VirtIO MMIO. Here you would have to by hand tell the SVSM, like, I changed the configuration. So either with a hypercall or with like a memory plus notification. So yes, you would need a different transport for the control plane, but the data plane would be basically the same as.
Yeah, that could be a good idea. So far we had only the vTPM, which is very, very simple, but maybe for more complex device, makes sense to move everything to VirtIO. Thanks.
So I think the most valuable thing for SVSM is about line migration and vTPM, right? So what is our current plan for the line migration? We know like AMD published their requirement for SVSM last year, right? So and now we saw a new PR. So what is the plan for the line migration? Like do we have any kind of plan for a common protocol and flow to host different CC vendors requirement, and also define those flow, maybe talk to the guest and also cooperate with the host. I think some kind of big picture everyone can fit in. So do you have a maybe, or can you share a little bit about that? Yeah.
Unfortunately, Pankaj is not here today. Was here till lunch, and he mentioned that he will send a proof of concept as soon as possible. So yeah, there is another PR, but it's very, very an experimental code, and what we won't really do is what AMD is trying to do. So yeah, I don't have a lot of information so far.
Is it fiction, or is it just no? Okay. I see. Yeah, it's just
kind of generic. I mean, it's not really specific to the architecture, as far as I get.
Completely shifting topics. On the SSH slide, are you going to implement it as in a tested secure channel, or is just as a vanilla SSH connection?
We don't have anything yet. This was more like an idea, if this would be useful, and then we can see how to do it. So there's no concrete concept yet.
Any news from OpenHCL about potential integrations and?
Yeah, no big news. I mean, Microsoft is really involved in the development of SVSM. They are also doing formal verification. So we are starting to support the user space. That I think it's a must to have for them. But yeah, I think one of the goals for us is to support paravisor mode using OpenVMM on top of SVSM. But yeah, I don't have much information, sorry. Okay, thank you so much.